mute yourself. Mhm. I can see it is. Okay, mute myself. Okay. Okay. Thank you. So we'll start off today's session. So we'll wait for a minute or so that people can join. Hopefully, they will join. And this session will be about week 11. I believe you might have gone through the content. How many of you have seen the content of week 11? Just give me the thumbs up maybe from the reactions tab. If you have. Okay. Okay. I can see three of you have just said yes, and the others I'm not sure if you have seen it or not. Very less strength, so I expect that uh, you will be having a conversation mostly. So now, in today's session, we'll talk about week 11, that is mostly around the DFS, and because DFS also follows a recursion kind of coding algorithm, so we'll discuss recursion as well. And also, we'll talk about because DFS is about searching something, so we'll talk about how search algorithm work, and in the same ground we'll talk about graph as well. So you might have heard the name of DFS and BFS during the lecture videos. You might have understood maybe, and also heard few of the things related to it. Okay, we'll discuss those things today. uh, as if you have been to my session, I mostly be using GitHub repo. I've shared the link in the chat, which you can open, go ahead and see that, uh, and see the topic which is written there. Okay, uh, I guess we can start now. If somebody is joining a little later, you can ask other to share the same link which I have shared in the starting. Okay. Okay, so I'll share my screen and then I will start uh, telling about DFS mostly and then the other things. Okay. So hopefully you can see my screen. If you are able to see my screen, you can just, yeah, thanks. I'll close this. And so this particular heading is about week 11, what happens in week 11. So it is about recursion, then DFS. There's something called as BFS as well, breadth first search. So that also will touch upon that. Also, there is a a natural analogy where whenever you are dealing with search algorithm such as DFS, they follow some pattern. So in this case, it is following a pattern called recursion. So it happens multiple times, something like that you can understand. So this notes you can use typically if you need whenever you want. Uh, yeah. So whenever you want, and before starting off about the content, we need to know few things in terms of what we will be talking about, right? So basic terminology which you should be knowing before understanding the topic which we are covering right now. So first is a node or a vertex. This is typically a point. Okay, so it is a point where something starts. So A, B, C, D, or any you can name it anything. So it is a point or a vertex in terms of graph. Okay, so graph is typically if you have collection of nodes. So you have points all together here and there, and then they are connected with the edge. Okay, so edge means a line going to other dot. So if we Try to understand. So if, let's say, if this is your dot, this starts here. So you have some other dot here, right? So sorry, in this place, right? So if you connect them, so let's say if this is the place, so if you connect these two pointers and then connect to some other point, let's say E, so it becomes a graph. So you are creating a graph there. So this becomes a node, this is the second node, this is the third node, and the line which is connecting both of them, it is a edge. Okay, so it is an edge. That means you are connecting two nodes or vertex or 2 points. Okay, so this is node, edge, and graph. uh, Typically we'll talk about neighbors. So let's say if this is one point and this is the other point, let's say C, so that means they are both neighbor. Okay, so these two particular points are neighbor. So if two nodes share an edge, they are neighbors. Okay, so these are the typical thing which you should be hearing, and you should be clear about those pointers. The other thing you might have listened to this point is adjacency matrix. So there is something called matrix, and in the same domain there is something called as adjacency. That means if a table, let's say, if a table that represents a graph connection, okay, some graph are connected. So let's say A is connected to B, that means A point has a edge to B, that means they are connected. And to show them in a matrix format or in a written format, we will be using adjacency matrix. Okay, to show them that there is some connection between the 2 points. You cannot be, it cannot be possible every time that you will be creating a dot and then connecting them and drawing a diagram. It is not really a good idea. So to avoid that, we can directly use a adjacency matrix, and so that we can use it in the codings and all, right? Okay, so if, let's say, I am naming this particular graph as graph. So graph, you can assume it as a dictionary or something. So dictionary or list or something like that. So you can assume that there is a key and there is a value there. So if I and J have some value, that means, let's say, A and B are having a value 1, that means there is some connection between these two pointers. So A is connected to B, so that means A has a edge between B. So A and B has a edge between them, right? So that you can assume. Is it clear what I've said, or no? It is not clear yet.
Yes, sir, it's clear.
Okay. So this is one of the terms which you'll be seeing, or you might have already seen. Okay. If I said it is a dictionary, so there is something called visited dictionary. That means a record of which nodes have been explored during DFS. So it, if I say visited dictionary, that means uh, a particular pointer or node has already been covered by my path, or whenever I was searching, I have covered this particular point, that can be A. So if I am saying A equal to 2, that means I have already covered A, and I can move on ahead with the other pointers. I don't have to search it again. So something like that, it might come in your uh, in this discussion. Okay, so visited dictionary is also one of the terms. uh, because we are dealing with something called as a graph kind of search, so there are two data structures you might be knowing. It is not like that you have to learn about this, but you are familiar with these pointers. That's why I'm just keeping it here, so that you can uh, create a new analogy based upon the things which you have already learned. So there is something called a data structure uh, stack, and the other one is queue. So this is typically used in programming languages, and we can, so let, just like list and dictionary and all, there is something called as stack and queue. Okay, so this is a data structure. They are typically used for searching something. So searching in terms of graph search. Okay, so stack, you can assume stack like uh, something is there in the table, let's say books. maybe. Yeah. So I put one book, then after that one more book, then after that one more book. So there are three books. That means this is a stack of book. Okay. So you can understand, right? So if there is a stack of book, that means I will pick the first book. Okay. So if I pick the first book, that means even though I have uh, put my book, third book, last one, let's say in the table, and at the end, if I can draw, give me a second. Uh, Not sure if I can draw. Give me a second. Okay. Share. If I can annotate here, uh, I'll try. Yeah, let's say this one book. Let's say this is a table. I put this particular book. This is my first book, and then after that, the other book I've taken here. This is the
Sir,
second book.
screen is not shared, I think. It's not visible what you are writing.
Is it now shared? Is it shared or no?
Uh,
Yes, sir. Clear.
So if I draw here, can you see that? This let's assume this is a table. At the right side,
uh, Sir, screen is not visible. Some pattern is
screen.
showing.
Yeah, yeah, so I am in the same tab where we are in the Zoom. So can you see the yellow color line,
Mm,
two lines here?
yes, yes, sir.
Yeah, so yeah, I'm writing here only. So assume this is a table, okay? Uh, and then I am putting books here. So first book I have put here. So this is one first book. The other book I am putting just above this. So assume this is a second book, and then again I have put it a third book here. So this is the third one. But now if I have to pick the book, I have to start from this one, right? The third one, isn't it? I cannot directly pick the last book, which I have put it in the first place. Are you getting it?
Yes,
What I've said?
yes, sir.
Yes,
Yeah.
sir.
So this is typically what a stack would follow. So this is a stack of book. That means the data structure stack also follows the same thing. So let's go ahead and see this. So uh, here it is written a stack is a data structure where elements are added and removed from one end only. So what is that one end? If I can write here, is it possible? Uh, okay, I cannot write. Okay, names. So if you are removing it, it can be from the only one end, because the other end which you have seen in the bottom there, it has been vanished. That means it is below some books. I cannot directly pick it up. It is not possible. That means you will only pick it up from the last one. So last one will be your first one to be picked up. That means it follows LIFO. That means last in, first out. Let's try to see that it follows or not. So when I say last in, that means third one was the last in thing, right? uh, yeah. So this third one was the last thing to be uh, put here, right? And then I am removing this one. That means last in, first out. Have you got the context? So this typically follows, the data structure also follows the same thing. Okay. Let's assume on the same ground. So let's assume you are trying to book a ticket. Let's say this is a ticket counter. Okay. You are the first person to be here. Then your friend comes, that is the second person, and then the other guy comes, the third person, and the fourth person here also. So that means this started, this one was the first, and this was the second, this was the third, this was the fourth. Can you tell me this, if this is a ticket counter, can you tell me which one of these will get the ticket first and get out of the line?
The first one.
First one, right? That means they were in a queue. So this is called as a queue. This thing what they are creating is a queue here for the tickets. The first one comes first and then he takes the ticket and goes away from here. That typically tells you about the queue data structure. That means the first one comes will go first only. So let's come back. Let's close this now. And if we come back, there's something called queue, and a queue allows adding one end and removing from the other end. That typically follows first in, first out. So this is the ticket counter example. So you have a line where you start off, and then if you got the ticket, you will be removed from that line itself. So first in, first out. So both these data structure are used by, so stack will be used by DFS and queue will be used by BFS. So this is typically how it will be followed. So keep in mind how it works, at least for this session. Then you can, if you want, you can forget about these things. But yeah, if you are going ahead with data structure and algorithm, you should be knowing how stack and queue works. And this is the typical question you will be asked in interviews and all. If you go to any interview, they will ask you related to these only data structure. Okay. So till this point, we have got an analogy, right? We have got an understanding how what are nodes, what are edge, what are neighbor, graph, adjacency matrix, visited dictionary, and then stack queue. These are the few things which you know by now. So let's come to the topic of the discussion where we started off. I'll just close it for now. So this is something which you might have already seen before. So if you have joined my session when I started off in week 1, week 2, I guess, so I told you you should be having a idea when to stop, right? So when I started off in week 1, I told you that even though you write a code, that's fine, but how will you decide when your code will stop will matter the most, right? So that comes to this week 11 as well. What I'm saying here is there is something called recursion happening here. So recursion means it is a technique which in which a function will be calling itself to solve the smaller version of the same problem. That means typically, let's say if you have one big problem and you want to subdivide it, so you want to divide it in multiple parts, then you can divide it, and when those parts are done, you can do the complete job itself, right? So let's say let me give you one example. Let's say if you have uh, a book to read, okay, so you have 100 pages. What you can do is you can tell 5 people to read the book for 20 pages each, and then they can tell you the summary of those, and then you can understand that yeah, this is the summary, right? So you give a task to somebody and it will do it for you, and then you will get that back and you will understand the crux of it, all 100 pages. It will be easier, right? It will be faster. So if you give the job in batches, maybe, so it can be 20 pages can be done in 2 minutes. So I'm assuming 2 minutes. If 20 pages can be done in 2 minutes, that means if you are going ahead with one task of 100 pages, that means 2 multiplied by 5, that means 10 minutes you will take. And if the same task will be divided by the 5 people, it can be done in uh, 2 minutes itself, right? So all of them will be doing in 2 minutes, right? So you can divide the task. But division happening like that is not the case here. Here, what you will be doing is you will start off, but you will keep on exploring things. Okay, that means if you are starting off with 100 pages, you will first start off with first page, then you can start off with okay, book reading is not a good example for this, but anyways, let's remove that book reading part. Let's come back to this, and then we'll try to create one example. Okay, keep that thing that it can be done in batches. One thing you should be clear, that if one task can be done by one person fully, it can be subdivided. So this should be clear. Then after that, we'll talk about the recursion. Okay, so let's say I have a task of maybe giving a factorial. Yeah, factorial is one of the easiest example. Or we can take an example of yeah, chocolate wrapper. I have created one example. Okay, let's see how we can understand. So imagine you have a chain of chocolate wrappers stuck together. That means you have a chocolate, but there are three or to four wrappers around that. Okay, so there is one particular first wrapper, and then there is some second, then third, and then the you get the chocolate. So what you will do? You will first look at the first wrapper. You will see if this is the first one. You will try to unwrap that, and then after that, what you will do is, when you get the chocolate, that means when you get the chocolate, you have to stop. This is the main thing, right? So let's say if you have just uh, unwrap the first layering of the packet, you have got the chocolate. That means you have to stop there. That's fine. So if you have got the chocolate, that's fine. We will stop there. So this is one of the conditions. So this is one of the conditions you will be keeping in your mind. The other condition is, if I get another layering of wrapper, I will continue to do the same. So continue to do the same means I will repeat on unwrapping that and then coming to the chocolate. I main aim is to get the chocolate, but I will repeat this task till the point I will get to the chocolate. So recursively doing the same thing, right? Till the point I get the chocolate. So typically, let's understand. I have a condition. If I get the chocolate, I will stop. Otherwise, I will keep on unwrapping the thing. So is this clear what I've said right now? So will you?
Yes.
Yeah. Okay. So let's see in terms of English, normal English, and then we'll talk about coding as well. So in terms of your course, there is the same case. What you will be doing, that means if I get a chocolate, I will stop. It is called as a base case. So where to stop is a base case. It is called as base case. A simplest form of the problem solved directly. That means if you have got the thing, you will stop there. So this is one of the if condition which you should be checking. If, let's say, we are talking about a list, that means if we have only one element, we will stop there. We don't have to do anything. We will return the same value which is there in the list. Okay, we can also assume that there is nothing in the list. That case can also be called as base case, because we are just stopping there. Both the case are okay. But now there is something called recursive step. uh, they call it as inductive step as well. Both of them are same. So what it typically means is, a problem is reduced to smaller instances and solved using the same function. That means you have created one function, that is fine. So there was one function for base case, good. Then there is one more function which will call this particular full function again till the time it will come to the base case. That means, let's again go to the chocolate analogy. If you have a wrapper, let's say first wrapper, you will get the chocolate, fine. If you have multiple wrapper in it, so you unwrap the first wrapper,
Sir,
you
you're
will,
not audible. The voice is, sir.
Yeah, I'm not audible.
You are not. You are, yes, sir. You are not audible. So voice is breaking.
Uh, is it still breaking?
Yes, sir.
No, sir. Clear.
No, sir, clear.
Okay, it was clear, right? Okay. Hmm. Okay, so yeah, let's come back to the chocolate thing. So that typically means you will again do the same thing. So I will say first wrapper I have unwrapped, but I have not found the chocolate. That means I will again call myself to check if it I have got the chocolate or not. So that calls a base case. If not, then I will again call myself to unwrap the thing, and then again check if I have got the chocolate or not, and then again I will unwrap till the point I will get the chocolate. So this is how it should be working. Typically, it is what it is written here also. So first look at the first wrapper. If it is the only wrapper, stop the thing. We have got the chocolate. It is the base case. Otherwise, remove the first wrapper and repeat the remaining chain. So recursive step. This is the recursive step where you will be repeating the same thing, and you will come back to the this particular base case where you will be checking if we have got the wrapper chocolate or not. So this is the basic recursion, how recursion will be followed. Any questions in this whatever we have talked about right now? No questions?
Sir, base case means we have to find. We have to reach till the chocolate. Means the chocolate we are considering as base case.
In this example, yes.
Yes, sir. Okay.
Okay. uh, Now the factorial example which I have just said, it has been taken in the lecture itself, so we'll discuss that and then see the pseudocode for it. So as I said, two things: first one base case, and the other one is recursive step where we'll be calling the same thing again. You can see here, this factor, if you talk about factorial, 0 factorial typically means 1 or no. Is it the case or no?
So factorial 0 is equal to 1.
Right. That means it we can take it as a base case. And if we have to find out a factorial of any number, we have to do something like this. So if let's say it is a 2, so 2 multiplied by 2 minus 1, and it is 1 typically. 2 multiplied by 1 is a 2 factorial, right? This is one of the other condition, right? So two conditions. Now we have to create a pseudo code so that we can understand if it is working correctly or not, and in terms of recursion, how to write the code. So the procedure's name is factorial, and we have to give a number. So n is the number which will be given. Then the base case is to check if n is 0 or not. If it is 0, that means we will return 1. Fine. This is the one thing. The other thing is, if it is not 0, n equal to not 0, that means we will check, we will do this return statement. So this return statement will do n then multiplied by the factorial n minus 1. That means it will again call itself and then again check if it is n equal to 0 or not. And if it is not, then again it will do the return, and again factorial will call itself, then again check, then again something like that. Sorry.
Sorry, I was unmute. Sorry.
Okay. Okay. So till the point we'll get to this point where n is equal to 0. And when you are getting to this point, let's say if you have got n equal to 5, till the point you have got to this place, it will keep on telling you the answer. So if you got to n equal to 0, that will return 1. Then after that, it will return to this. it will multiply by this and it will return the other value, and then it will return the other value, then it will return the other value, and then at the end will be returned as a one typical value. So let's see what I've said just now. Let's assume factorial 4 was called. So typical behavior should be, I will check here if it n equal to 0 or not. So 4 is not, that means I will go to else condition, and it should return 4 multiplied by factorial 4 minus 1, that is 3, right? So this is what it should return. Because factorial was already called again, so that means I will go again check if it n equal to 0 or not. If it is not, then I will go to else condition, and then I will get what? So n is now 3 and factorial n minus 1 is 2, so that means 3 multiplied by factorial 2. So this is the second line which we have got. Then again we will call 2, so n equal to 2, n equal to 0 or not? No, it is not. Then it will go to else condition, then it will call 2 multiplied by factorial 1, and then again because this is 1, I will again call, I will get this 1 factorial 0. Now we have got n equal to 0, that means it is equal to this, it will return 1. Now it will keep on multiplying this, so I have got 1, so 1 multiplied by 1, and then I will return this. So because this was called, I will give the return value 1 here, and because this was called, I will give the value 1 multiplied by 1 means 1. Then because this was called, I will give the value 2 multiplied by 1, that means here 2 will be there. Because this was called, I have to write 6 because 3 multiplied by 2 is 6, and because this was called, I have to return 4 multiplied by 6, that is 24. Have you got what I've said or no?
So can you repeat the last step? How you go from back?
From back.
I mean from base case to factorial 4.
Yeah, so let's say I called, right? So I'm calling from here, from it this line, I'm calling this particular procedure. I've got this context, I'm
Yes, sir.
calling it, but I have not got the result.
Yeah.
In this, I am not getting any result. That means I am getting one particular statement which is coming from this return statement. That means it will call again this factorial. If it is being called, that means it will get one more time this kind of result, not a value which we were expecting, right?
Yes, sir.
Then it will call again. So this should be called, and then it should call this. It will get this, not a result. Again, if I go for factorial 1, it will give me this kind of return statement. It is not a result, right? At the end, because I have this factorial 0 being called, I have a base case here. I will get 1 for it. Because I have got 1, now I can return the other values as well. So I will keep on getting. So I have got 1, so I will give it to this particular factorial 0. It will multiply. So 1 multiplied by 1 is 1. That means
Yes.
now this answer what I have got, let's say 1, it is for this one. Are you getting it? So this
Yes, sir. Yes.
answer what I have said, it will be for this. Now I have to multiply it by 2. That means it is 2. 2 for whom? For this
Goes to
guy.
factorial. Yes, sir. This
Yeah.
it will become 6.
Yes. So 6,
Okay,
6
got it,
will
sir.
be answer for this, and then I will
Okay,
multiply
24.
and I will, yeah. So this last one. So it is not getting the result in a sense, that means the answer. Let's say if I want a factorial, I'm not getting 24, I'm getting a return statement saying call something else. This is what I'm getting. So I have to call something else. Otherwise, I will not get the answer. Okay. So now we have got a context how recursion can happen. It takes time to understand these things, so you have to practice about these things, so you get familiar and then you can answer them. One of the example is the list example. It is also from the lecture itself. So sum of element in a list. This is the problem statement which you have. So
Sir,
first one, yeah.
sir, in the previous example, why we are going back in back direction? So from base case to factorial 4.
So let's say I ask you to uh, give me a pen. Okay, I ask you to give me a pen,
Yes,
but you tell me the store name where pen is there, right? So you just tell me the store name. Have I got the result what I wanted? If I ask you for pen,
no, sir.
no, right?
Yes,
Then if I go to store, you have just suggested me to the store. I go to store. Then I ask them also for a pen.
yes,
They show me a direction that there is the pen.
yes,
I've still not got the pen. Okay. Then after showing the direction, somebody else takes that pen box and put it after me. But still, I have not got the pen. Are you getting what I'm saying? So here, when I ask for a 4 factorial, I have not got the factorial of 4. I am getting something like this.
yes, sir, yes,
That means because this was said to me, I have to check that also. So it will go to this. And when I ask for factorial of 3, it doesn't give me the factorial of 3. It gives me this. So that means now I have to check for factorial of 2. Are you
yes,
getting it?
yes, sir.
So till the time you get the result, the answer for one particular thing, you will keep on exploring that. And so because you have got a result at the base case because we have set it. So even though your procedure starts, you have to end it somewhere. So this ends on the base case,
Yes, sir.
right? So if you've got the result, that means you will just keep on getting those things, and then this is a pattern which you are following, just a recursion thing. So you will keep the answer to this, it will create answer for this, and then it will create answer for this, and then same thing goes on. Are you getting it what I've said or no?
Yes, sir, I understood, but you have explained that from base case to factorial 4. So
Hmm.
going back in back direction, you were saying something. I was asking for
So,
that.
so in
Hmm.
fact, factorial 4 value, we are getting the wrong value of it. And we know that the factorial 0 is 1. So that is the right none.
Uh,
Sir, for getting value, we should check in back direction. Uh,
for for checking values means,
Value means factorial 4. What is the value of factorial 4? We should check in back direction.
see, when I am returning a function, that doesn't mean I have got the response correctly, right? Are you getting it? So if this statement returns me a procedure itself, that means I have to complete this thing. Otherwise,
Yes,
this
sir.
whole thing
This is
won't stop anywhere. Yeah.
Yes, sir. This is clear. We have to start from factorial 4 and end the procedure at
Hmm.
base case. So this is
No, no,
clear.
no. Ending. No, no, no. So you're not getting it. Ending at the base case is not the thing. Here, because you have called multiple times the same procedure, you have to give the answer to it, right? You are calling factorial 0 also. Whenever you are calling factorial 4, you have just called 1 2 3 4 other procedure as well. You have to give answer to them, not to directly to the factorial 4. You cannot give directly. So you have to give the answer to them, and then they will give the answer to factorial 4. So this is not a straightforward way. So you are just creating a new function for others, and they will give you the detail.
Yes, sir.
Yeah, so you will get the base case answer, that is just this. Because you have created it for every function. Whenever it, let's say, factorial 10, 20, or any other factorial will be called, you have to go to this base case. That is the main thing. You have to end it somewhere, and then it will reverse the thing. So it will give you the answer, and then it will give you the answer, then the other one, and then
Yes,
at
sir.
that.
Yes, sir. Yes, sir. I understand.
Yeah.
Yes.
Okay. Okay. So let's take one more example, and then let's try to see if this works or not. So there's something called first and rest, which you have seen in the first part of the this course, where you talk about list. So if you have a list, first value of that list can be called as first of L. Assume L is a list, and the later part is called as rest. So let's say 1, 2, 3, 4 is your list, and if you call first of L, that means you will be getting 1. Okay, 1 you will get, and then if you call rest of L, that means you will get 2, 3, 4. So this is what you will be getting. Have you got the context what I said?
Yes, sir.
Yeah. Now, so from that scenario, we'll try to do sum of elements in a list. So we have a list now. Now we have to create a recursion code for this thing. So we have to do the sum of the list. So from your analogy, what should be the base case of this list? So if I have to sum something, what should be the place where we have to end in terms of recursion? What do you think? Will it be like this, where we have returned 1, or something else? Because you can see, obviously you have seen the dog, but yeah, is this correct? Returning 0 is correct, or no? Is this base case what I've created is correct, or no? Should we have anything else other than this, where I am checking the base case as, if you have empty list, just return 0? Do we need to
Maybe
change?
it's correct because the list is empty, so by default it is the value is 0.
Hmm. Any other opinions?
Yes, sir. It will be correct because list is empty and no one, no num. There is no any number in the list.
Yeah. So let's say if I return 1, what will be the issue if I don't return 0? If I return 1 here and not return 0, what will be the issue? Anyone?
Then it will return 1 because if the condition meets, or then it should be returned that value whatever you given this.
Yeah, that means, see, the thing is, because I have said we want a sum of elements, it cannot happen that empty list will have a 1. That means, how can it, a empty thing can have a sum of 1, right? If there is nothing, how can it be 1? It can be only 0 in terms of summation. But if we have to give a multiplication of element, then what should be the return statement here for an empty list?
One, sir.
Why?
So because we cannot multiply by 0. If we multiply by 1, then it remains the same.
Yeah, correct. So that's why we are using return as 0 here, because this is a sum. If it was multiplication just like this, we would have taken this base case as 1. Here also we are multiplying, but it is a factorial. So let's see. So let's see how it is working. So first of all, we have a list. We are checking if list is empty. Just give a return statement as 0, because there is nothing in that. So there is no summation. So it will be 0. Otherwise, we have to do something. So we have multiple element in one of the list. So that typically means if I can annotate, hopefully, okay, I'll see this. So a list has one, two, three, four. Now, what is the way of giving a summation whenever we have to do it one by one? So, what we can do is we can start off with 1 plus 2, or maybe we can start off from the last, maybe. So, that can be 4 plus 3, right? So, if we start from here, it can be possible, right? But how will be adding the other values? How will you get that? Is the question. Mostly how we will be dealing with the other one. So 3, what about 3 and 4? So what we can do is we can start off, because this is a recursion, we can start off with first value. So we have one value, that is 1. Good. Now because we have rest 3 values there, we can add them, but one by one we have to add. So what we can do is we can again call our function itself. So I will call this as L1. Okay, so this is my L1. L1 has 2, 3, 4. Okay, so L1 has
Sir,
2.
I can see
Yeah.
so many screen.
Ah, I can also see so many screens.
1, 2, 3, 4, 5, 6, 6
It,
screens, sir.
it is infinity, so it's fine. So can you see this part? Is just see the first one. Uh, okay. Should I create something? Oh, wait. Now can you see this white screen?
Yes, sir.
Yes, sir.
Okay. Hopefully we can write there. So if I write L equal to 1, 2, 3, 4, can you see that?
Yes, sir.
Yes,
Okay,
sir.
good. Okay, so we have this list now. Because we have to add all of them, we can start off, let's say, from maybe 1 we have. Because these are 3 values, we cannot directly plus them with like this is not possible, right? But what we can do is assume this is a new list. Sorry, assume this is a new list which we are creating. So we call it L1. So L1 equal to 2, 3, 4. This is our new list. Now, because we have a new list, we might have to do something like 2 plus 3, 4. Is this correct? Do you think this is correct way to do that? We now have lesser numbers, so we can try to do this to 2 plus something. Is it correct or no? Yes, no, something.
Yes, sir.
Yes,
But
sir.
because this is one is a value, integer value, and this is a list, we cannot directly add them. So let's call this a L2. So L2 has 3, 4. Now we can try to add them. So let's assume 3 plus 4. So now we have one element here, but it cannot be added. So what we can do is, what should I do? Can you just tell me? What do you think? What should I do? Should I create a new list? Call it a list
Empty list.
three, empty list. Okay. So let's assume this is a empty list now. But we have to do something, right? So 4 we have, the value is 4, but we have to do a summation with empty list.
No, sir. 3 plus 4. And
3 plus 4.
yes, sir. 3 plus 4, and we can consider empty list.
Uh,
We have
so from here, let's try to see. So I said 1, and then 2, 3, 4. We have created this a list, right? Isn't it?
yes, sir.
Then we have created, so because 2 we have taken, we have created these two element as a list. So should I do this 4 or empty? What do you think? Just from starting, see 1, and then the other values are list. I cannot directly add them. So I have created list 1. Now list 1 has first value, and then the other values are there. So I have started off with 2, when I have created a new list called L2. So 3, 4 are there. Then again I have one value. I cannot directly add a list value to 3, right?
Yes, sir. So we
So
can
that means L3 is my list where we have 4 or empty list.
consider empty list.
Are you sure? Try to follow the pattern. So this is my list 1. Then we have list 2. Then we should be having list 3, right? For this, or just empty list.
What we want actually here? What is the question?
The question is, if I give you this list here, can you add them all in one go? Is it possible? So can you add one with the other
No, sir.
element of
No,
list?
no,
Is it
no,
possible? No, right? So we have
no.
to divide them upon multiple lists, so that we can get to the end and then we can add them together. So this is what we are doing. So we have started off with this. We have created this a new list. Then we have a new value. This is the first value which we have. Then we have rest values. We are keeping on going down to this place where we get to the empty list. So right now we are in the list 3 here. Is it correct to have a list where 4 would be there, or only empty list should be there? This is the question. From
Uh,
here,
Empty
where
will
should
be
we?
not possible because then we'll not get the answer. If the list will be empty, then we'll not get the answer because we have to add all the
So
element of the
4 will
list.
be there for L3. The list
So there is a
only.
condition called, if the list is empty, let's assume this is what we have list, then I will call it a 0. This is a 0. You can give 0. This value, if there's something called list 4 equal to empty, that means it will return 0. This is what I will give you. This condition I have given to you. Now, what should I do? So this empty list will give you 0. So 4 plus 0 is possible.
So my answer is 4.
So this is your very good. Okay. So now at the end, what let's see what we have done. Let's use some other color, maybe red. I'm not sure, but yeah. Okay, so we have started off with this value. We had L, 4 values. Then because we were not able to add a integer with a list, that means we have created a new list, that is L1. And then we have started off going to the L2 part. Then we have got this value. And then because this is also a list, this becomes this 4, 4 along with the list. Now we have to deal with this. So L3 is now this. Because I can take one value, that is fine, but add with whom? I will add with empty list. That means this is a new list which we have. So L4 is the new list. And I'm saying I can give you a condition where I can return 0 here. That is fine. So I will give you 0 for this. Now you can use this in the previous statement. So I will have this particular statement which can become 4 plus 0, and because it is 4 plus 0, that means 4. I will again go back, and because I have got 4 here, I can use it here, right? So 3 plus 4, that means 7. Now I can use this here, so it will go here, 7, that means
Sir,
But why we are doing this?
why we are doing this means
Means why we are going back and adding, means our execution is 4 plus 0, L4 equals to 0.
our question was this, right? You have a list called as 1, 2, 3, 4. Give me the sum of elements of this list. This was the question, right? You have to
Okay,
give
okay,
the
sir.
sum of the elements,
Okay, sir.
right? So we have to give the answer, right? Yeah, that's why we are going to 7. So that means 2 plus 7 is my answer for this one. So 9. We have got 9 for this. That means we will go ahead and so to this, and 1 plus 9 at the end, and typically L. So sum of element would be 10. This is what we are getting. Have you got the context? So because you have to add upon elements, you can subdivide them in parts. Are you getting the thing or no? Uh, it was
yes.
just missed. Okay.
Yes, sir. Yes, sir.
Okay, let's see. So because let me share the screen again. Because we were talking about something as this, we are using same thing here. So what I'm doing is I will be giving you, if list is empty, that means it will return 0. If it is not, then I will start off. So first value of L I will take. Okay, so first value of L I will take here. This is the first L, that means 1 plus list sum and rest of L, that means 2, 3, 4. Right? Have you got the thing?
It's 9.
Yeah, no, don't directly jump to the answer. So you have got a list now which is having 2, 3 as 2, 3, 4 as the value. Now because I am calling this list sum again, this procedure
Yes,
again,
yes, sir, got it.
you will come back again, right?
Yes, sir.
So same thing, whatever we have done in this particular thing here, PDF or something. So this is following the same trend, and this is how the recursion works. Okay, this is the same pattern where you'll be seeing every recursion algorithm working like. So you have to follow the same. Okay, I'm assuming you have understood this thing, so that I can just move on. We have to complete the thing, other things as well. Okay. Yeah, so main thing, the important thing, the base case must be clearly defined. That means this should be clearly defined so that it can stop at certain point, at one point it should stop. Otherwise, recursion will not terminate and it will keep on doing the same thing again and again. Okay. So if, let's say, if I have not given this thing to you, so if this was not given, that means L4 empty list will be 0. If it was not given, what will you do? There's nothing to do then. It keep on going to same thing. So there is no first, there is no first, there is no rest in this. In this particular empty list, there is nothing. First, rest, anything is not there. Right. So you have to keep on doing the same thing, and it will end up on crashing your computer, and it won't work. Okay. The other thing is the input must get smaller with each recursive call. So that is it happening in your case. We had a 4 element here, then it become a 3 element, then it become 2, then it become 1, and then at the end empty. That means it was doing the same thing. So the input should be getting smaller with each recursive call. The last point is recursive function suspend their computation until the recursive call completes. Okay, so everything is completed, it will stop there. Okay, so everything completed means you will have to answer it. So you have to go back and then go back and then go back, and then at the end you will get the 10 value, and then it will stop there. Okay, so it has to complete everything. You have called multiple times this list sum, you have to complete that, then only you will be stopping. It cannot happen that you will come to this place and then you will stop. It won't happen. You have to come back to the places where we have called you. Okay. Yeah, hopefully you have got the context. Yeah, let's go ahead. So this recursion thing is typically followed by DFS as well. You might have heard about searching algorithm. So you have to search something. Let's say if you have you want to come to IITM, so you will search on map. You will see from railway station which road should go to IITM, which road is faster, which covers uh, let's say if in between you have to cover Marina Beach, and also you will go to that path and then you will come. So you will search for something, right? So there are few algorithms which can be used to search something similar in similar manner, BFS and DFS. So DFS is typically depth first search. It search for every. So let's say if you want to search the shortest path, so it will search for every element straight, and then it will come back and then check for others if they have the sorted one or not. BFS checks by uh, the neighbors. So you have two neighbors, it will check first them, and then it will go to the other neighbor, and then it will check them. So it is breadth first search. So level by level it searches. So you can assume like, so if you are starting from here and you have two nodes here, and then let's say if you have two nodes here and yeah, one node here. So what you will do is, as a depth first search, you might be taking this route and then coming back. If this has, so let's change the color. So assume you start from A, you will, because you are using DFS, you will go to B and then go to C, then go back to B and check if there is any node here or not. If that is not, you will go back to A again, and then you will check any other node is there or not. Because let's say D is here, you will get to this again, you will go to E, and then you will check if there is another node or not. You will come back to D and then again check this place, F. This is the DFS way of thing. Okay. And the other way would be, other possibility is, let's try to erase that. And the other thing would be, So what I do is I will check, I will call it D. So I will check both of the places, B and D first. I'm done. One level done. I will again go to, let's say, from B. So B will check for another level. Only C is there, so this will check for only this. So this level is done. Then I will check for not level. This part is done. So I will check for these two, and then let's say if there is some other element, then I will check for them. So level by level. So this one level is done, and then other level, and then the third level. So this is done by BFS. This is how it will search. Okay. If you're not understanding too much, it's fine. It's okay. For the first time, if you're listening these things, it is completely fine to not understanding everything. You can keep on exploring these things. You can also search in Google. Let's say if I DFS and BFS data structure. So you can go ahead and read about these things. Uh, by example, maybe there are website where you can just directly do the traversal. Uh, Not sure which one. I have used it to understand myself, but yeah, you can search on Google. You are better than me for searching, so you can just search for that. Okay. Try to explore and you will understand. Let's come back to this topic. As I said, BFS start with initial node. So initial node was this one A, and then it visits all the neighbor in one distance. So assume this is one as is one distance. So it will visit all these two, and then it will go to other neighbor distance to all these, and then after that all of them. It will continue level by level. On other hand, this depth depth first search, do something else. Why I have told you about Q? You can assume something like Q. So assume like 1, 2, 3, 4. So what you will do is, let's assume this is one level, right? So you are done with this one, and then if you are done, it has got the ticket. You will go to second level, and then if this is also done, you will go to third level. If this is done, then fourth. Have you got the context what I said? How Q works similar to BFS?
Yes, sir.
Yeah. So same analogy is here. Okay. Let's talk about DFS because this is in your course, so you should be knowing. Now, uh, DFS works like so. Even though let's say A, B, C, D, hopefully this looks like B, and E is there. For these kind of tasks, it is fine. It will go till this point. Then, but again, it will check for D if it has any other value or not. Again, it will check it has any other value or not. Again, it will check, and at the end, again, it will check. So that means if I have F here, I have maybe yeah G here and H here, something like that. You can assume. So I have to come. I will go to E, then I will come back to D. Then I will check here. I will check here. I will check here. So if I have got in B, I will check for this. So I will go to H. Okay, and then I will come back, and then I will come back here, and then I will check F and G. You can see, right? Even though A has a neighbor closer to them, so that means F and G were there closer there, but it checks till E. This is the typical behavior of depth first search. Okay, even the task can be assumed that you should be checking neighbors exactly first, then go to other one, but it doesn't do that. It will go to one of them directly at the end. It come back, keep on checking, and then at the end, if you got it, then it will check the other neighbors. So this is how it works. So same thing, I have just written it. This comes from the lecture itself. You can just go ahead and watch the lecture if you have not till this point. So it starts off with one node. You can assume this is a I node. Then it visits a neighbor that assume at J. Suspend work on I and explore J instead. So that means this. So now I will go to B, but I will not go to F and G. I will now explore B itself. Okay, it is I, it is J. I will go to J, but now I will not explore I anymore. I will explore J, and then I will, if I'm done, then I will do the other one, and then I will do the other one, and then at the end. So this is typically like that. So suspend the work on I, explore J instead. Continue until reaching a node with no unexplored neighbor. That means it will go till that point where you don't have any neighbor. So E don't have any neighbor, so it will come back. Okay, so it will backtrack. They call it backtracking. So backtracking to the nearest node that still has unvisited neighbor. So if it has any unvisited neighbor, it will backtrack to that point, and then it will repeat the same scheduling and all. So typically you might understand. Now let's go back to the point we talked about stack. uh, this is one book, this is the other book, this is the third book. That means this was starting point, this was the second, and this was third. That means i will I will pick up this third one first, right? So till this point I will go, I will pick up, this is done, then I will go back to the other one. So if this is picked up, that means then I can go to 2, then I can go to 3, even though 1 was the starting point for me. Are you getting it? And any kind of uh, have you understood what I said, or it was just going?
Yes, sir. Yes, sir.
Sir,
Yeah,
can I ask one question?
yeah,
So, like in this diagram, H is with also associated after B. So, can it go before going to C? Can it go to H first and then return and then go to C?
yeah.
Because
It is, yeah, it is fine. So let's say if you don't go to C, it can go to H. It depends basically on the weight of the this edge,
okay,
how much weight it has.
okay,
Let's say if this has 2 and this has 1, and this has 2 itself, so I will, because the weight was lesser here, because I was finding a shortest or the simplest or the lesser weight path, I will go to B. So assume you have two options. I'll just draw here. So B has two options. It has one H and C. If I give this as weight 3 and this is weight 1, I will go to H, explore that first. It depends on the age weight mostly.
okay,
So these algorithm mostly are creating a shortest path, or where you are having less consumption of something, right? Any element.
okay, sir. If
Yeah,
weights are not given, then it can go both way.
yeah. It is up to the whoever is doing that. It can go to H or C. It depends on that. Yeah.
Okay, sir. Thank you, sir.
Okay. So two things. Stacks we have understood. Yeah. It at the end we will call it, and then the other one, then the other one. One more thing you can assume just like this. So I said it will do the backtracking after getting to E. It will do the backtracking. That means, isn't it the same thing what we have done in the recursion? We gave to the we gone to this point, and now we are recurring. We are backtracking, right? We are going back. Something similar is happening in DFS also. Have we got the context? Are you trying to match that recursion and DFS?
Yes, sir.
Yeah. So this is what we have. DFS by natural meaning, it follows stack kind of a environment, and also the recursion both. And BFS, bets for search, follows a queue in its domain, where it checks for level by level calling. Okay, okay. Let's see the diagram. One of the diagram. This is typical. I'm just giving one simple graph, and if I, let's say if I do a BFS in this, so I can go to C or B. It's fine. It's fine. So I will go to, let's assume I start off with B. So A, B, and then I will go to D. Then I will again backtrack. So D will go to B, and then because B don't have any other thing, it will go to A. And then after that, I will go to C and then I will go to E. Then again I will check there is nothing. I will go back to C and then I will go back to A. So that's it. This is what the backtracking is. Okay. Okay. So this is one of the procedure or pseudocode what was given in our lecture. Hopefully I have not got anything wrong. Uh, yeah. So this is our code. Okay. So let's try to see what is written here, and then hopefully, if we are not able to understand, that's fine. It's okay. You have to explore this and then find out yourself that if it is correct or not. Okay. Let's try to read this first. So because we have understood about data structure like dictionary, we can use it here. Okay, we have also told or talked about adjacency matrix. Something similar will happen here also. Okay, so this is a dictionary, or we have to also keep on tracking the visited numbers, so we'll be using a dictionary for that. That is called as, so DFS maintained dictionary called as visited to track explode node. So we have to keep the track of those things, right? So I have created a procedure called DFS. It will take your graph, and it will also take a dictionary called visited and I, from where you will be starting off. Okay. So what it means is, so I can be, let's say, A. So visited I equal to 2. In the starting itself, I said I have visited A and I will start from A itself. So because you can see from this part I have to start somewhere, right? So I will get in the starting itself, I will start from A or I can start from D. It's up to the logic, right? So it is like that. I can start from A. Okay, assume you can start from I is your
Graph is a matrix.
no, graph is not a matrix. How graph can be shown as a matrix? It can be like that. So you can see I've used one example of where is adjacency matrix. Yeah. So this graph can be shown. So if A has a node to B, that means you can store 1 here. Okay. So A has a node to B and B has a node to A. That means I can store here. So this is a graph reflected in terms of adjacency matrix.
Okay, sir.
Yeah. Okay. So this was the code. Okay. So I have written that this has been true. This is okay. Now I will run a for loop here. So for each j in columns graph, so because we have to deal with a column and row kind of formatting, so columns graph, if graph ij is equal to 1, that means if I is connected to j, this j, so A is connected to B, if there is a node connecting, there is a edge connecting both the nodes, and is not a key, there is no key of j, then I will do something. I will do something means visited equal to, I will call myself and then do the same thing. So TFS will call, I will get a new graph and then I will visit j. Uh, here it is true. That means it will visit j. That means let's assume what I'm saying. I will start from A. Good, because this is already visited. This is already visited. Fine. I will check for other values in what, in graph. Okay. J can be, let's say, B. I will check for B. Now, if there is some node A to B, which is there, A to B is there, and it is not there in the visited dictionary, that means it is not visited yet. B is not visited yet. Now, what I will say is keep this dictionary, okay, keep this dictionary and then explore B. That means now it will explore B. It has a new key called as visited B equal to true. That means now we have visited B as well. Then again, same, follow the same trend. And now you will check for the column. I will check for the column called what? I will check for D. J will be D now. So I will again check if there is a node or not. If it is not there, I will just skip it. Or if it is there, I will go ahead. Hope it is not confusing yet. Let's try to see something like this. Sorry. So I have taken one example, but I might have to go to slides. So this is one of the example which was taken in the session. Uh, yeah, something like this. So you are starting from 4, assume like that. So you're starting from 4, you've called DFS graph visited 4, visited will take 4 as true. Now it will check for the value. So we are counting it by 1 2 3 4. So 4 has 3 nodes, 1 5 8. That means 1 is the first one. So I will explore from here. So 1, I will go there. I will call it again, just like in the code it was written, graph visited 1. Then I will call a equal to true. Are you getting it? I am calling a equal to true because I am not now here. Now I will check if there are nodes connected with 1 or not. So there are 4 which is already visited. So I will ignore that. And then there are 2 and 3. So because 4 and 3 these are coming after 2, so I will go to 2. Okay, I will start off with 2. I will again call it. So this will be called visited j equal to 2. Now 2 will be true because I have not visited that. Now I will check 1 and 3 because 1 was already uh, given here as true.
Then
Yeah.
I will not suggest that.
कुरकुरे कुरकुरे अब सोचे क्या बेटे बार ऐसा सोचे
Okay. So am I audible?
Yes.
Good.
Yes, sir.
Yes, sir.
So yeah. So now because I have already visited, I will not go there. I have only one option left, that is 3. So I will visit that. I will call again DFS. Now what do you think? What will be added in this visited dictionary?
214.
3. And then then
3.
again we will start from 4.
3. Oh, yeah, very good. So because 3 will be now true, we don't have anything to visit here, right? There is nothing. Okay, so I will go back to what? I have gone to 3 from where?
4.
2.
2,
Yeah.
right? Yeah. Yeah. From 2, I will go from 3, I will go to 2. From 2, because it was from coming from where? It was coming from
1.
1.
1.
1. So I will go there and then again I will go to 4.
4.
Now I will explore something from 4. What should be the next value I should explore because 1 is already done?
5.
5.
5.
Yeah. So here I will explore 5. So it is written here. Now I will go to 5. How should we follow from here? So from 5, where should I go?
6.
6,
6.
right?
6 or 7.
Now not 7 because 6 is after 5 itself. So 7 is bigger than 6. Yeah, so after that, after 6, if you're saying 7, then yes, then we should go to 7. Then after that, after you have been visited to 7, what should we do?
Backtrack to
Back
6.
to 6.
Yeah, back to 6 because there is nothing to be explored. So I will go to 6. From 6, where should I go?
8.
8.
8.
5. Oh, 8.
5 was already, yeah. So 8, right? So already 7 was done. So I will go to 8 now. From 8, where should I go?
9.
9.
9.
9.
Okay, so 9. Then after that,
10.
10.
10.
so it goes to 10. Then after that, it will backtrack. So because there is nothing to be shown here, so it will backtrack to 9, 8, 6, and yeah, 5, 4. Then that's done. Everything is visited, so we are done with DFS. So this is here the
Sir,
DFS
sir,
algorithm.
Sir, but
Yeah.
in the
what kind of
pseudocode, it is
question there
harder.
will be there? Means to related this graph means what kind of question they will ask?
Uh, it it can be something. It should be written over there. So you will be given a graph. There they can ask you. So you might have some question, right? Have you seen any assignment question? Is it graph question or not?
Not yet, sir. I'm trying to understand.
Mm, there should be some graph question. If it is not there, yeah, oh yeah, yes. So see, this kind of question will be asked. Okay, so you have been given a graph, and then a this is the same kind of coding which we have just understood. So for loop will be there, if condition will be there, if there is no key present in that particular dictionary which you are sending, it will create a new one, and if it is already there, that means it will call for DFS. So
It is saying that graph is a matrix. How we know that this graph is means we know directed graph, undirected graph, but we don't know that graph is a matrix.
so you can assume, so just like this, if I give you this detail, you can create a graph, right? Can you create a graph? So I am saying to you, a and b has value 1, that means a is connected to b.
Yes, sir.
Assume like that. So let's try to do this. uh, I guess I need some space here. So you have to help me create a graph. Okay, I will just tell you the details and then you will help me. So when I say A is connected to B, so A and B. Now, if I'm saying connected to B, that means what should I do?
Make a arrow.
Yeah, right.
And C is also
Because
connected to A.
yeah, so C. So I should give a arrow. Yeah,
Yes, yes.
because I'm not giving you here like this. That doesn't. So this is not a what? What do you think? This is just not saying that it is only connected to C. But here when you see C is A, so that means like this. So both are connected, both ways. So if you are writing both ways, so you can directly write A, C. This is also correct. If it is only going in one direction, that means let's say if it was A to C 1 and C to A 0, that means this is what the graph should look like. So typically you can create a graph using this matrix, and by using this graph, let's assume base sorry b and c. So this is your graph. Now if I tell you to create a matrix, will you be able to do that? If I write something like this, a b c, a b c, if I ask you to do that, can you tell me? So from a to b, so
Uh,
from a to a, is it connected? It is not, right? It should be 0.
0. Yes.
So then if A to B, then
1.
1,
A to
then
C 1.
1, and then B
B
to
to
A,
1.
and B to B
B
is
to
0.
B 0, B to C
C,
0,
yeah, C to A.
C to B 1, and C to B 0 and 0.
Yeah, right. So you can create. So both looks almost similar. You can just create from graph a matrix, and from matrix you can create a graph.
Thank you, sir.
Uh, where was the question? So something similar will come in the exam as well. So you will be given a graph, the code, and then you have to answer based on the code what is given there. So typically it is about adding some new element to the dictionary, and so it will be easier if you just do these kind of questions. Yeah. So yeah, something similar it will come. You will be given these details. Okay. Should we move on ahead?
Yes, sir.
Okay.
Yes, sir.
Yes.
So till this point we have understood we can create an algorithm which can search for something. We can work with graph. We can also do backtracking in terms of recursion and all. Uh, this recursion is typically when we call something again and again. So calling something again means calling itself again and again. So this is called as recursion, and there should be a stopping criterion. So stopping criterion would be returning widgeted. Okay, so it will return a widgeted dictionary at the end. If everything is done, it will return a widgeted dictionary. This is what the demand was. That's it, right? So this is the DFS part with the recursion. You can read about this again so that you can understand more if I'm not able to make you understand. Okay. So this is the relationship between them, and this is the summary which you can just read out and understand what was there in the session. Let's do one question maybe so that we can try to explore a little bit about recursion and all. Have anyone of you tried any question from practice assignment?
Not yet, sir.
Not yet. Okay,
No,
let's
sir.
try the first one then. I guess we can do this. Mhm. Okay, so this is the same practice assignment. Okay, let's see the question first of all, and then try, because I'm talking about recursion only. So this question is about mostly be about recursion and all. Okay, so this is unique. Something unique means it is a procedure called as unique that takes a list called L. So here it is. If I do this plus, yeah. So assume this is calling a list L, means it will get a list L. The main part here is it returns the unique elements in the list. That means, let's say if I have L and 1, 3, 3, 5, 7, what do you think if I say unique element in this list? What are the unique element in this list?
So 1357.
1357.
Okay, is it like that? 1357. Okay, so it says it returns a unique element in the list after removing the duplicate. That means this will be removed. Uh, but I asked you only till this point. You have answered me till this thing. Yeah. So the question what I asked you was, if you have this, what do you mean by if I say give me the return the unique element? That means the answer should have been for only this would have been like it returns 1, 5, 7. These are the only unique, right? Till this point. So it returns the unique elements. Keep, so see, Even though you have read this question previously, in the exam, it can be a possibility where it can be changed. You read this unique and then you think that yeah, it will be the same question asked in practice assignment. It cannot be also. Okay, so before going directly to the conclusion, try to listen or read the full thing, right? So I have only asked you the unique element, not the list here. I just want a unique element. Okay, okay. So that's it for now. So the this question is asking for a list of unique elements, removing this. So if this line was not there, removing duplicates, it would have been 157 only. So it will return the unique elements only. Okay, now let's come back to the code. So we have three things written over here. When we see, first it creates a new list. Okay, init elements. Okay, that means initialize the element or initial element. Then there is one condition called as if length is smaller than 1, smaller than equal to 1, length of list. So right now the length of list is 5, it should be smaller than 1. So it shouldn't go, let's assume, let's say list has 1. Now will this condition satisfy? If we have a list
Yes.
that is 1, yeah, right? So if list is this, then will this condition satisfy?
Yes, sir.
Right, so that means it will return the empty list itself, and this will return the first one. So this is this condition is typically satisfying uh, the base condition in terms of recursion. Okay, now this question is asking us for the main condition where we have the inductive or recursive values, right? Inductive, this was the base, right? Now we have the inductive. Again, what we are doing is we are creating something here. It is saying init elements, init L. What do you mean by this? You have already seen something like this. What do you mean by this? Is it a, will this init of L give you a element or a list? What
List.
will it return?
List.
The remaining of
A
a
list.
rest function.
Remaining of the rest, or
It will give the list except the last element of the given list.
so assume this is a list. What should it return? L of 1, L equal to 1 or L equal to 1, like this. Assume this is your list. This one or this one should be written here.
Right.
Line number. This one? Hmm? Yes, no?
Let me know here.
Yes, sir.
Yeah, okay. Okay, so we have a list here. Assume like that. Because it was an empty list, we can now assume it as 1 maybe. And then we have to start from here. We have to write something. So let's see the options first, then uh, let's see if we can fix it or not. So what it is saying is uh, something as member. Member is not written here anyway. So something as member, and then init element and the last of L. It looks correct, right? Init, it is taking 1, and then it should check for last. Is it right or no? If we talk about last, do you remember what is last?
So 5.
So do you think this is correct way to interpret or no? Should we take 5?
Yes, we can.
Okay, okay. If I take 5 and then call unique with the other elements, assume, let's say if you are saying this is 5, and this is because it was 1. So will it be a integer or it will be a list itself also?
The initial items
Integer.
will be,
Integer, okay, 5. Then I have to give this list to this unique.
sir, why we have taken only one? Sir, initial items are 1, 2, 3.
Uh, in this line I asked you guys, right? So what should be initial? Somebody said it will be integer and somebody said list. I asked you one. Will it be one or it will be everything here? Are we confused
It will
how?
be everything up to 5 because it is the
Yes,
init
sir.
function.
Yes, sir. 1,
Okay,
2, 1, 3, 5.
let's
1,
go
3,
back
3,
to
5.
wait. I might have covered it in week 6. So this is what we had, right? Are you guys there? Let's recap. So this should be important because we are dealing with rest, first, last, in it, right? So we should be knowing what should return what. Okay. So I'm assuming you know now, all of you, not few. Init will return a list. It has everything, just not the last one. If you want the only the last one, what you have to call? If you only want the
Last.
last one, the last.
The
Right.
last.
Okay. Let's come back to the question again. So let's move this for now, and 1, 3, 3, 5. We have this list now. Only the last value is not here. Okay, assumed like this. Now let's go to this particular option. This first option is saying we have, yeah, so let's assume this as 1, 3, 3, 5, and last will give what? Integer or list?
Integer.
Integer
Last
7.
element integer.
Yeah, good. So I will again call this list with unique. So unique, and these elements. Okay, fine. What is else condition is doing? It will return something unique and again this plus last L. What was the criterion? What we wanted? Returns a unique element in the list after removing the duplicate. Is this particular code removing anything?
No, sir.
Okay. Let's then, if it is not removing, let's go ahead and see the other option. Almost similar kind of option, but it is not calling unique anymore. It is just giving initial element and then last and then returning the initial elements list and returning this. Is this also correct? We are not dealing with anything related to unique, but we should have, right? I told you that we have to call ourselves in the inductive step. Do you think this is correct in that manner when we talk about recursion?
No, sir.
No, right? So it should be wrong in that sense because we needed an inductive step where we are calling ourselves. Okay, let's go to third option. It is also similar, but here it is not written as unique. In the first option, you got unique here, and here you are not getting unique. Okay, let's see the last option, and then we'll try to configure what is happening here. Almost similar, but it has, so here this is only integer plus plus a something, right? It will return something. And let's see what is the return value here. So this is a list or not? L is a list here or not? This L, what is this L?
This is the list.
Yes.
This is a list, right? Now, if something is written here, can I do this plus plus L? This is integer or a list?
Integer.
So if this returns a list, let's assume this is a list, it is integer, I assume 7 maybe. Is it possible?
It should be list also. No?
Yeah. Okay, let's see this option, almost similar, but it is now a list, returning a list. Sorry, you have got the answer. Anyways, this is the list. Same kind of options are there, A and D, and here it is a list. From the option, I didn't have to run any algorithm. From option itself, I have just neglected the other options. Have you got how we have just managed to do that or no?
Understood, but I have a doubt.
Yeah.
In the question, can you come up? In the when we have initialized the empty list init elements, there is a condition, if condition, length L less than equal to 1. It returns L.
Yeah.
So if any procedure returns something, then it automatically conclude that, right?
Yes.
Nothing will go further that this condition, if there is
It won't go
the
anywhere.
list contains anything greater or equal to 1. Sorry, less
Yeah.
than
So
or equal.
if the length of list is, let's say, if you have L equal to 1, it should return this list itself, because only one is there and it is unique. It should be unique. And let's say if it is empty list, it should return that also, because there is nothing to be checked, right? So it will return the same list.
Okay,
So it is
then
handling both the condition.
in that case
Now,
it was you.
yeah. So now let's say if I have multiple values, I assume 5 values, I have to check, right? Because this condition won't satisfy, right? It won't satisfy. So I have to go to other condition and check if there is something we can do. We can check for the values, and because when you see the option, let's assume D is the correct option. So we have, what we are doing here is we are doing something which is creating a new list, right? Here we have started off creating a new list with the lesser element. Are you getting it? That means it is removing something somewhere.
Okay, by using the init function.
Yeah, correct. But are we removing the correct thing? We have to check that. So that's why these if and else condition will be there. Okay, so we have to do that. Okay, let's do one thing. Let's try to do a check if we are getting something removed or not. So I'm just removing this. Hope. Okay, let's assume we start off. I am assuming we have the code now. D is our correct answer. Is it doing the thing correctly? Not here. Okay, so if we start off with list equal to 1 3 3 1 5, what should be the value we'll be getting? 1 3 5, right? Is this should be the correct value we should be getting, right?
Yes, sir.
Okay, let's try to do that. Let's check. So we are giving L to this and then creating a new list. And after that, a condition will check. So it will not be correct because it has 5 values. I will again go here. So what should I write here? What should be written in place
Sir,
of?
1331.
1331.
So this is the value which we have. Let's assume this thing. So I'm not sure what member does. Anyone has seen what member does? Is
Member
it?
will check the element is there in the list.
Just
No.
like key function.
Okay. I have not added in the document. I will add maybe.
The is key function.
Yeah, okay. So member will check for last of L. Is it the case?
Whether
Yes,
it
the
is the
element
member
last
of
of
the
L is
elements or
the
not.
member of the list init element.
So this is what we have: 1 3 3 1, and last of list is, I guess, what was that, 5?
Yes,
Yeah,
5.
last 5, right? So it will
Sir,
be,
I think for this question we have to take a sorted list, right?
I'm not sure. I'm just taking randomly a list. Let's see if it works or not. It is not mentioned in the question itself, right? It is a sorted list. A list, it is saying. Let's see if it works or not. Okay. Okay. So it is checking if 5 is there in the list or not, right? Yes, no?
Yes.
Yes, sir.
Okay. Because 5 is not there, we will call unique again. So unique now will be called for a new list. I will just call it U, and then the list is 1 3 3 1, and I will end it and close it here. So I will call it again. So again it will go. I have to check because I have to, if it is a procedure. So it is not smaller than 1. So I will go ahead. I will again create a new list, which will be called as
133.
1 3 3, and this is the new list. Okay. Now let's go back and see. So new list which we have created just now is 1 3 3, and last of L, are you okay?
1.
1.
Good. Yeah, so from, because the L is this, right? I'm sorry. Yeah, because the new L which we have got is this, it has a value 1 in the end. We will check if this condition is not satisfied, it is not satisfying exactly. So I will go to else condition. Are you guys with me? Have you got what I said? I will go
Yes.
to else condition. Okay. Then I will again do something. I will call unique. I will call it U. So U, and then the list which we have 1 3 3, and in what was in it for us? This one, right?
That's it. That's it.
Yeah. So this is what we have, and plus plus last of L.
1.
Last of L. Uh, but what it is doing that? 1.
No, other way around. For the 5, it will go to the else. For the second one, it will go inside because 1 is a member of the list.
Uh, didn't get you. What?
Sir, in the
This
first
member
step,
in it
we
last will give true because 1 is a member of 1335, right? The first element is 1. So because
Oh,
this is true, it will go to return.
okay. So we have got it incorrect, is it? In the previous place, in this?
Yeah, the first
Yes,
one, it
sir.
will go to
5
the
also
else.
needs to be
Yeah, that's
added.
why okay. That's why I said what is number. I didn't know. So 5, this condition was not correct at the first one when the first iteration happened. It will go to else.
Yes, sir.
Yes.
And 5 will be added.
Why you guys did stop me there? Okay. Anyways, so let's assume we have not done anything. Let's just remove this and yeah, assume this is that. So we will, because 5 was not the member of it, we will ignore it. I will go to else condition. Uh, Initially it was that, so it will take 1 as well. So 1331, and this is the last value. We are appending the last value to this, that is 5. I will call this again. I will go back. I assume this is the new.
Yes.
Yeah, okay. I will come back here. I will check for the last value. So that would be U133, and this list closes. And then again we have 1. So it is there. So I will call directly unique 133. So again I will go back to that particular position in the code. It will it will not return anything. It will just create a new list, and it should be 1 3, right? Yes, no?
Yes.
Yes, sir.
And again come back to this place. So is it a member of not? I have to check. So uh, 1 3, and
Three.
last of L is 3. So it is a member. So I will just call unique of 1 3 here. Again I will go back and check. Yeah, it is not satisfying. So I will create a new list. I'll use some other color maybe. Yeah, so new list, it will only be having 1. Uh,
Yes.
yeah, okay, good. So I will come back here. I have to check for the last one. So this is what we have for now. So 1, and this last is 3. So sorry, ignore this. So this is 3. That means it should go to
Else.
else. Okay, good. So unique of 1 should be called, and what was the last of L?
3.
3. So it will go back. Because it is only one value, it will return the list itself. Okay, so this is very messy, but let's see if we can come together. So this will return a list itself, 1. So plus plus 3, sorry, again, because this is a list, again I will go back to plus plus 5. This is also a list. So at the end we will get 1 3 5. Yeah, we are getting it. So this is correct. Have you guys understood, or it was just a
Recursion
bouncer.
is little hard
Yeah.
to understand.
Yeah, it is little hard. If we would have, I would have just remembered what member means. I would have, maybe it would have been easier. But yeah, so this is the main thing. The return thing is the main part. I would ask you all to go ahead and try practicing these things from recursion as well as from the graph part. Both of them, both the things would be. Uh, yeah, one second. Both the things should be clear. The other question you can just try out. This question might be a good question which you can try out. Palindrome. Yeah, calculate is easy. Two question I would suggest what you should be doing is from week 11, at least twice you should be doing. So you should be doing this question, palindrome. It is very good question which you can understand how it works. And the other question was we have discussed earlier about this graph. Okay, try to practice these two questions. It will be, hopefully you get the things. Okay, so that's it from my side. Any questions you have?
No, sir.
Yeah. Okay, cool. You can use this particular document for week 11. Any document which you can, if which you want. And yeah, if you have any doubt, you can just ask. If you are on discourse, you can ask there. Tomorrow you won't be having a session, so you can have a good Sunday maybe. Okay. Bye. Good night, everyone. Thanks for joining.
Good night, sir. Thank you.
Yeah. Bye.
Good night, sir.